Hello class. In lesson 210, you will learn to apply the fundamental theorem of algebra to find the zeros of a polynomial function. And this is going to result again in finding complex zeros. So in the previous lessons of 2.7 and 2.8, we found again the zeros of rational and irrational zeros, real zeros. Now we're going to look at complex zeros. Now, just to remind you again, the imaginary unit, I, is defined as the square root of -1. So I is equal to the square root of -1. And a pure imaginary number is written in the form of bi, where b is a real number and I again is the imaginary unit. So we get those again as a result of taking square root of negative values, as you see right here. Like the square root of 16 is 4, but the square root of -16 would be 4i. And again, similarly with -9 and, of course, -1. Now, so what this means that, again, like I just showed you, that if I want to take the square root of -9, well, since the square root of +9 is equal to 3, the square root of -9 would simply be -3. I'm sorry, 3i will be 3i, not -3. What am I thinking? 3i. And the same thing with the square root of -144. Since the square root of positive 144 is equal to 12, then the square root of -144 is 12i. That's it. Now this again rule still applies to irrational numbers. So if I'm trying to simplify imaginary units where I don't have a perfect square, like 32. Well, 32 can be divided by 16. I can break up 32 into the factors of course, the negative, 16, and 2, since 16 times 2 is equal to 32. So I follow the same strategy if I was looking for, again, a positive number and look for the largest perfect square factor, again, the largest perfect square factor of that irrational radicand. So here 16 happens to be the largest perfect square factor of 32. So as a result, the square root of this negative is going to be I. The square root of 16 is 4, and because 2 is not a perfect square, that's going to stay in the radicand. So we end up getting 4i times the square root of 2. And we could do the same thing again with 18. Since 18 can be broken up into -1 times 9, 9 happens to be the largest perfect square factor of 18, and 2, I do the same thing. The square root of the negative is going to be I, the square root of the 9 is going to be 3, and the square root of radical 2, well, that's going to stay as the radical 2. Of 2, again, doesn't get simplified. So that stays inside the radical. So our answer is 3i times the square root of 2. Now, we're going to use, again, this strategy in order to simplify and find zeros of polynomial functions using, again, the idea of the fundamental theorem of algebra. Since f of x is a polynomial of degree n, where n is greater than 0, then f of x has at least one 0 in the complex number system, which means, again, if you remember, the complex number system is any number that's written in this format, which doesn't necessarily mean that every value has to be written like this. We could find a complex number where the b value is equal to 0, all right, getting only the real parts, or the vice versa. The a part is equal to 0, getting only the pure imaginary value of the complex number. Or, again, where a and b are not 0, and they're just equal to any number, again, not 0, which, again, writes as it looks like this, the standard form of a complex number. Now, the corollary, which, again, is just a lighter version of a theorem, states that any polynomial function of degree n has to have exactly n zeros. Whether they're repeated zeros or unique zeros, but they're going to have exactly n zeros in the complex number system, which again relates to this idea that it could look like this, or it could just be this part of the complex number or this part of the complex number. Okay. And with this fundamental theorem of algebra, we have the linear factorization theorem, which states that as a result, because we can have exactly these number of complex zeros, then we can write any polynomial as the factorization, linear factorization of those values. So any polynomial can be written as n linear factors. So if I have x to the third power, I can multiply 3 linear factors to get this polynomial. And again, where these numbers, C1, C2, and Cn, again, are going to be complex numbers. And again, whether that complex numbers falls into this format or just simply the A or simply the pure imaginary value unit, the pure imaginary number. So let's see some examples of this, all right, and how we're going to find these complex zeros. So first, again, since we have x to the third power, I know there has to be 3 zeros, and one of those zeros is going to be a rational zero. So we're going to use our rational zero test to find that number first. So 1, -3, 7, and 75. And we're going to look for the factors of 75 here to test. There we go. To test and find out what works. Now the factors of 75 are going to be pretty long. There's a long list, so I'll just write a couple of them. Well, 75 could obviously be divided by 1. It could be divided by 3. It could be divided by 5. And of course, the list is a little bit longer. I'm only going to stop right there and only try those from this list here. And specifically, I'm going to try -3. See if -3 works. This is now positive 18, which is now 25, and yep, -75, which is equal to 0. So -3 is going to be one of our zeros, one of our rational zeros. And then as a result, we have x squared minus 6x plus 25. Now, normally, again, I would rely on my factorization to figure out what's going to make the quadratic factor now equal to 0. But unfortunately, there are no factors of 25 that are going to add up to 6. And because they both have to be the same sign, they both have to be negative in order to add up to -6 and multiply to a positive 25, nothing works. The only factors of 5 are 1 and 25, which doesn't add up to 6, obviously, and 5 and 5, which again doesn't add up to 6. So factorization is not going to work. And therefore, the only other thing that works is going to be the quadratic formula. So this is the only thing that's going to work. Let me just copy this. So this is the only thing that works. So that means that A, B, and C are going to be 1, -6, and 25 respectively. So plugging this into my quadratic formula, we're going to get that A is equal to -1 times -6 plus or minus -6 to the second power minus 4 times 1 times 25. And then 2 times A, which is 1. So we have 6 plus or minus, and again, plugging this into the calculator, I'm just going to plug all of this into the calculator. That's going to equal to a total of -64. So 6 plus or minus the square root of -64. Well, 64 happens to be a perfect square, positive 64. And since the square root of positive 64 is equal to 8, the square root of -64 is going to be 8i. So dividing 6 and 8 by 2, we get 3 plus or minus 4i. So there are zeros. So our zeros are going to be the following. X is going to equal to the rational zero of -3, and x is going to equal to the complex zero of 3 plus 4i. So these are the 3 zeros. And again, This is still considered to be a complex number. It's just missing again the imaginary part, because the imaginary part is 0. So if I want to write this number as a complex number, I would just simply put 0i, and that would make this look like a complex number. But we don't do that because, again, it's redundant. So there's no reason to put plus 0 because nothing really changes in value. So there you go. Let's do the next example. So again, let's practice the next example. So the next example, we're looking for the factors of 10, which are 1, 2, 5, and 10. And we're going to test, let's test 2. So this is 2, -4, -8, 5, and +10, so 0. And again, I'm just going to jump straight into using my quadratic formula, not even bother identifying the factors. And we're going to end up with -1 times -4 plus or minus the square root of -4 to the second power minus 4 times 1 times 5. And 2 times 1 yet again. Now, again, plugging this into the calculator, make sure that you put a parentheses again around -4 before raising it to the second power. Do not make the error of not putting the -4 in parentheses, because without the parentheses, raising it to the second power is going to end up giving you a -16 if you're using the calculator. If you do it by hand, then you should have no problem, and you should end up with +16 regardless. Okay, but plugging it all into my calculator, I'm going to end up that this is going to simplify to -4. And well, the square root of -4 is similar to the square root of +4, which is 2. The only difference is that because of the negative, we have an imaginary unit, so we end up with 2i. And just like the previous example, I can divide 4 by 2, which is 2. 2 divided by 2 is 1. So here is our imaginary 0, our complex 0. So 2 plus I and 2 minus I. So our zeros are 2, that's the rational one, and 2 plus and -i. So these are the 3 zeros to this polynomial function. So moving on to the next example, finding the rational 0, we would get the factors of 55, which are 1, 5, 11, and 55, and divide those by the factors of 3, which are 1 and 3. But again, I'm just going to simply stick with getting the factors using the positive values. So 1, 3, I'm sorry, using the integer values, so no decimal values. So just dividing all of these by 1. And let's test +5. Let's test +5. 5 divided by 1, 5. So -3, -13, +1, -55. Bring down the 3. That gives us 15 and 2. This is going to give us 10 and 11 and +55 and 0. So 5 works. And again, jumping straight into my quadratic formula, x is going to equal to -1 times 2 plus or minus the square root of 2 to the second power minus 4 times 3 times 11. Divide this by 2 times 3. We end up with 2 plus or minus all of this simplifies to -1, -128 divided by 6. Now let's do some side work over here. The square root of +128 is not a perfect square, but it does have a perfect square factor, specifically 64. So if I multiply 2 with 64, that gives me 128. And since the square root of 64 is 8, that perfect square, I can write the square root of 128 as 8 times the square root of 2. Now the only difference here is because it's a negative 8, it's going to have just that imaginary unit. So x is going to equal to 2 plus or minus 8i times the square root of 2. And then factoring a common factor among these three, which is 2, I can divide those three numbers by 2. I get 1 plus or minus 4i radical 2 divided by 3. So there are my zeros. My zeros is going to be that x is equal to positive 5, and then the complex 0 of 4 plus I times the square root of 2 divided by 3, and 1 plus 4i, 1 plus 4i, and then 1 minus 4i radical 2 divided by 3. So there are my answers. And let's do just the last one. Now the last one is a degree 4 polynomial. So that means we're going to have to use synthetic division to hopefully find 2 rational zeros. And then we can jump into the quadratic formula to find the remaining 2. So the factors of 20 are 1, 2, 5, 1, 2, 4, 5, 10, and 20, and of course positive and negative. But we're just going to jump into and test 2. Let's test positive 2. So we have 1, negative 5, negative 2, positive 6, and 20. And again, the factors of 20 are 1, 2, 4, 5, 10, and 20. And from that list, I'm going to pick 2. You know what? Let me make this a little bit smaller, so I don't take up too much space. So bring down the 1, and this is going to become 2, negative 3, negative 6, negative 8, negative 16, negative 10, and negative 20, and then 0. So we found one of them. We're going to have to do this again because this factor is a degree 3. So we're going to do it one more time. And from our list, let's pick 5. So this is positive 2, 10, another positive 2, 10 again, and 0. So there. So now, having done this second time, now we have our quadratic factor, which again, we can just simply jump into our quadratic formula and have A, B, and C be 1, 2, and 2 respectively. So x is equal to negative 1 times 2 plus or minus the square root of 2 to the second power minus 4 times 1 times 2. Let's divide this by 2 times 1, so just 2. And we get negative 2 plus or minus the square root of negative 4. This all simplifies to negative 4 divided by 2. And again, since the square root of 4 is 2, the square root of negative 4 would be 2i. So we end up dividing both the negative 2 by 2, which is negative 1, and the 2 by 2, which is also 1. So here's the complex zeros. So our zeros is that x is going to equal to 2, x is going to equal to 5, and x is going to equal to negative 1 plus I and negative 1 minus I. So these are the 4 zeros of the polynomial function. And technically, I can define again these things as all of these can be considered as complex zeros, because 2 can be written as 2 plus 0i, and 5 can be written as 5 plus 0i. So technically, they're also complex zeros. So there you go, 4 complex zeros. And again, they follow again, and they follow the idea of the fundamental theorem of algebra, right? It's still again within that definition that all polynomials can be written as a linear factors, and they're going to have exactly one complex zero. In this case, 4 complex zero, at least one complex zero, which in this case again is exactly 4 complex zeros. Well, there you go, class. This concludes again the examples on lesson 2, finding the complex zeros of polynomials. If you do have any questions, please send me a message through Remind or email. And again, thank you for watching, and I hope you have a great day.